Hi and welcome to the Windows System Programming Fundamentals course here on Pentester Academy. My name is Pavel and I will be your guide in this course. Hi and welcome to Module 1 Windows Foundations. In this module we'll take a look at some of the basic concepts in Windows. We'll start by looking at processes and then virtual memory, DLLs, threads. We'll take a look at the general Windows system architecture and then briefly discuss the various Windows APIs in preparation for the next module where we'll actually start writing some code. So let's start with processes. So a process is a management object that encapsulates a set of resources that are used to execute a program. So a process manages something like a virtual address space, and so every process sees a flat virtual address space of some size, which we'll discuss a bit later, and this is where memory is allocated, DLLs are loaded, and so on. We have something called an executable image, which holds the initial code and data the process needs to execute. We have a handle to kernel objects, and so once we try to access some system level objects such as a file or a mutex or another process, we need to get a handle to that object, and that handle is stored in a private handle table within the process. We have something called an access token, which represents a security context of the user running the process, which encapsulates information such as which process, which user is it, to what groups does it belong, what kind of privileges does it have, and so on. This is used for access checks, for instance. When we try to open a handle to an existing object, this may fail if we don't have the appropriate access. And finally, we have threads. And so threads are the actual entities running code. And so when a process is created, the first thread is created with it, that eventually is going to run our main function. So processes are isolated from one another. So one process cannot write to another process by accident or corrupt another process by accident. That, of course, by design. Let's take a quick look at processes in Task Manager. So I'm going to open Task Manager by pressing Ctrl-Shift-Escape. And there are several ways to open Task Manager. And so in Task Manager, there's a Processes tab here. But this tab is not that useful in my opinion because it has very limited number of columns and some of them are a bit confusing. So I'd rather look at the Details tab. So in the Details tab you can see various columns related to processes. So let me go over some of these columns. First we have the Name column. So the Name column is the image name, the executable name on which this process is based on. Most of the names here are actually executables, but some of them are weirder, such as a system and secure system and registry, which are special processes created by the kernel, which we won't be looking right now. And so normally what we see here is executables. However, the executable itself is not the identifying property of a process, because we can have several processes, like we can see here, that are running the same executable. The actual identifier of a process, which is unique for a process at any given time, is the process ID. So this number cannot be the same for any two processes that are currently executing. And then we have this status column, which is very kind of weird. What does it tell us? There are actually three values here: that's running, suspended, and not responding. So suspended is something that is typically found when we're working with UWP processes. These are the store applications we can use in Windows 10. So for instance, I'm running calculator here, the new calculator in Windows 10, and we can see it's sort of running, whatever that may be. And then I minimize calculator and notice it becomes suspended. And so now when such an application, such a process goes to the background, such as when it's minimized, then all its threads are suspended so it doesn't consume any CPU. And this is very similar to the way things work on the mobile world. If I go ahead and restore calculator, it becomes running again. So this is the common occurrence of having processes suspended. So what does running mean? That really depends on the type of process. If the process has any user interface, then running means that the user interface is responsive. And so the thread that manages that user interface is looking at its message queue, and if something comes in that message queue, it picks it up and takes care of it. The other option is not responding. Not responding happens when a process that has any user interface, the thread that manages that user interface doesn't look at its message queue for at least 5 seconds. And then Task Manager concludes that it's not responding, and typically you can see the window becoming a bit blurry or faded, and the not responding text is added to the title bar and so on. Nobody likes not responding applications. For processes that don't have any user interface, the only valid value is running, because from Windows perspective, it doesn't really know what that process does. Even the process can do nothing. Maybe it's stuck on something, and maybe the process is just currently calculating like crazy various stuff. It doesn't matter, it will always be in status of running. So Windows really doesn't know what that process is doing and what's its actual state. There is no way to know that. Then we have the username column indicating which user runs that particular process. So most of them are running under my user, but there are some special users such as system and local service and network service, which are used to run Windows services, which we'll briefly discuss later in this module. Then we have the session number, which is 1 and higher for logged on users, and 0, which is used for the system. And so session 0 always exists, and it's the one hosting services and system processes. What exactly does a session hold? We'll discuss that probably in a later course. Then we have the CPU time, and we have some columns related to memory. The default one that is shown if you just go ahead and run Task Manager is this one called Memory Active Private Working Set. And if you have a bit older version of Windows 10, you'll see something like Active Working Set without the word, Private Working Set without the word active. In any case, this indicates the amount of RAM used by the process for private memory. That is memory that is not shared with other processes. And so this is generally not a very good counter to look at if you're trying to understand whether your processes are leaking memory, for instance. The good column to look at is called commit size. You can right click, select columns, and add commit size. By default, it's not added. And so commit size indicates the private memory which is committed to the process. Some of it may be paged out, some of it may be in RAM, but that's the actual memory used by the process for its private purposes. And so in some cases we can see there's a very big difference between commit size and active private working set. In this case we can see a Visual Studio process where the active working set, it looks like 280 megabytes approximately, but in fact that instance of Visual Studio allocated much more memory. Just some big part of that memory is not currently in the active working set, maybe paged out. But still, if I want to understand how much memory this process consumes, commit size is the good column to look at. And that's unfortunate because this column does not appear by default. And then I added some other columns here like the base priority of a process, which we won't look at right now, and the number of handles that you can see here in its private handle table. I mentioned that every process has its own handle table, so this number shows us what number of handles exist in that process. We don't get the details of which handle points to which object, but you just get the actual count. We'll look at how to get the details in a later module. And then we have the number of threads here, which is number of threads in that particular process. We expect that number to be at least 1, because as we mentioned, when a process is created, one thread is created along with it. And then I also added the platform column that shows whether that process is 64 or 32-bit and some description. And we'll discuss the differences between 64 and 32-bit processes in terms of how we program against such processes in a later module as well. And so every process has a virtual address space. And so the address space starts with address 0 and ends at some maximum. The term virtual memory means that when I have a pointer to something in my process, when I access that, it may be the case that it actually resides in disk. And if it does reside in RAM, I have no idea which address in RAM it's in. And technically, I don't really have to care. The memory manager is the one taking care of all of that. And so everything in virtual memory, or in physical memory for that matter, is managed in chunks called pages, and the default size is 4 kilobytes. And so from the CPU's perspective and from the memory manager's perspective, everything that is allocated or not allocated is always in chunks of 4 kilobytes. And so from a processor's perspective, when a thread there tries to access some memory, let's say I'm calling a very simple function such as malloc, I get back a pointer to some memory. When I need to access that, I just make the access. The memory manager will map that to physical memory as appropriate, and if it throws that memory to disk, then when I try to access the memory and a page fault exception will be raised by the processor, the memory manager will catch that exception and get that data back to RAM, fix the tables, and tell the CPU to try again. So all this from user space is completely transparent. Here's how it may look like in principle. So let's say I have two processes here, process A and process B, and we have a single physical memory because that's RAM, it's always a single entity in the system. So let's say I want to allocate some memory, so I allocate a page or some pages of memory, and they may be mapped to a physical memory. Let's just assume that. And then I can go ahead and access and allocate more memory, and so on and so forth. And so we can see there's no direct correlation between virtual address spaces and the physical memory where that memory may be stored. And of course, if there's some memory that I've allocated but haven't used in a while, the memory manager is free to throw that page or pages to the page file so that that RAM is available to other processes. If we take a look at process B, the same ideas apply. Each one can allocate memory even in the same addresses in virtual memory, but they don't necessarily correspond to the same memory in physical memory, because this is just private memory for that process. However, it is possible to share pages. You can see this middle page here is shared by these two processes. That in fact is fairly common for things that are shareable, such as DLL's code. And so code is read-only by definition, and so it's easy to share. So all the processes using the same code can share it in physical memory. So we save physical memory because physical memory is precious. So what sizes are we talking about when we say that each process has its own address space? So for 32-bit systems, each process gets 2 GB of user address space by default. And so each process has its own 2 GB of potential address space. It doesn't mean this entire address space is taken. It starts out almost empty. While the process goes ahead and loads DLLs, allocates memory, and so on, this space starts to fill up. And that's the limit, 2 GB per process. So if we say something like, what's in address 1000? Then the next question should be, in which process context do you mean? Because each process has its own address called 1000. The other part of the 4 GB potential address space in 32-bit is 2 GB of system space. This is the memory used by the kernel and all kernel device drivers running in system space. Now, because there's just a single kernel, this address space is a singleton. It's the same one no matter from which process you look at, which kind of makes sense. And so these addresses in the upper 2 GB of the address space are actually absolute, so they're not relative to which process I'm looking from. On 64-bit systems, the idea is the same, the numbers are just different. And so for user mode, each process has a gigantic address space of 128 terabytes. This is really a lot of address space. We can't really fill that kind of address space today because that would require amount of RAM plus page files to be around 128 terabytes. So there's a lot of potential for address space. And the system also gets its own 128 terabytes of system space. Again, that doesn't mean the kernel uses all that memory. It can't, and no kernel on Earth would be able to exist with such amount of occupied memory, but this is just potential address space. If we take 128 terabytes and add another 128 terabytes, we'll get to 156 terabytes, which is very large, but not large as the potential 64-bit address range can get to. So 2 to the 64th power is 16 exabyte. So exa is something that we get by taking tera and then peta and then exa. And so the potential address space in 64-bit is really huge, and today cannot be used because of limitations in the hardware. So current hardware supports 48 bits of virtual address space, and that gets us to 156 terabytes as we've seen. I will say that on Windows 8 and earlier versions for 64-bit, the address space supported is only 8 terabytes for user and kernel space. And the reason for that has to do with an implementation detail in Windows, which was fixed later in Windows 8.1. So that's the values we get today. One of the other important concepts in Windows are dynamic link libraries, or DLLs. DLLs are loadable modules, which means they can be loaded from files and mapped into a process's address space. They can contain any of the following. They can contain code, global variables, that is data, and resources such as strings, icons, and so on. And they're naturally shareable between processes. And many DLLs come out of the box in Windows, many of which expose the various Windows APIs which we use when we write applications. And these DLLs are typically shared, as we've seen earlier, in physical memory. So here's an example. Let's say we have two processes here, Notepad and Paint. So let's say Notepad comes up. It has its own executable code that needs to be mapped to somewhere. Let's say it's mapped to RAM in this location. And then it uses something like kernel32.dll, which is one of the subsystem DLLs, which is very important and used by practically all user mode applications, except for native applications. And so it's mapped somewhere in physical memory. So let's say we have a Paint process, and the Paint process has its own executable code. It may be mapped to the same virtual address as the Notepad process, but it's a different address space, so there's no connection, and it's going to be mapped to a different location in physical memory. But MS Paint also needs kernel32.dll, so it's going to map it to exactly the same location in physical memory. So they're sharing the code in kernel32.dll, which is very good, because if we have dozens of processes all needing the same DLL, it would be very wasteful for all of them to get their own private copy in physical memory. And so it doesn't happen, and they all share the same copy in RAM. And that was, of course, super important in the early days of Windows NT, when RAM was scarce and very small. If we take a look at other DLLs in a similar vein, like user32.dll, which is also used by Notepad, but it's also used by Paint. And so again, they're going to be mapping that DLL from the same address, by the way, in their virtual address space to the same shared code in RAM. And so DLLs are used to, on the one hand, create libraries, which we can use, but on the other hand, they're very important when we want to share code between processes so that physical memory is saved. In the next video, we're going to look at threads.